Taking a physical jar of seawater back to a laboratory for chemical analysis takes days, if not weeks. But a toxic algal bloom can suffocate a coastal ecosystem in a matter of hours. The sheer volume of modern pollutants compounds this problem. By 2040, an estimated 17 million metric tons of microplastics will enter the oceans annually, accumulating alongside relentless, deliberate oil dumping. By the time a lab analyzes a physical sample and identifies a critical spike, the ecological damage is already done. You cannot mitigate a rapid environmental disaster using data that is weeks out of date. Managing this volume and velocity of contamination requires abandoning the laboratory bottleneck entirely. The solution is a real-time, four-dimensional monitoring stack, an interconnected network of sensors spanning from the seafloor up to low Earth orbit. This new marine nervous system operates across three distinct layers: sensors bolted to the seabed, autonomous mobile platforms patrolling the surface, and radar satellites monitoring from space. These tiers are engineered to communicate continuously. They link microscopic chemical changes at depth directly to macroscopic surface anomalies, tracking across miles of ocean. To understand how this architecture functions in practice, we have to look at how it is actively being deployed to monitor one of the most highly trafficked and stressed marine choke points on Earth. The Egyptian coastline and the wider eastern Mediterranean basin present a uniquely volatile operational environment. With extreme commercial shipping density, massive runoff from the Nile Delta, and expanding deep-sea gas drilling, this region serves as the ultimate stress test for a live monitoring network. The foundation of this stack is the benthic layer. When engineers lower a multi-parameter sonde into a highly polluted zone, like Abu Qir Bay, which absorbs over 180 million cubic meters of untreated wastewater annually, it must operate entirely on its own. Traditional lab analysis relies on consumable chemical reagents to test for pollutants. A submerged sensor cannot be constantly refilled. To survive long-term deployments, these devices substitute chemical reactions with direct physical and optical measurements. For real-time heavy metal detection, the industry relies on a highly precise electrochemical technique known as stripping voltammetry. The process begins with pre-concentration. The sensor applies a cathodic electrical potential to a graphene electrode. This acts like a magnet, pulling positively charged ions directly out of the seawater to accumulate on the surface. Next, the sensor reverses the scan. This strips the metals back into the solution. As ions detach, they generate an electrical current directly proportional to the exact concentration of the metal. Chemical concentrations only tell part of the story. Sensors must also tackle physical pollutants, specifically identifying microplastics using flow-through impedance spectroscopy. By shining polarized light and measuring the electrical resistance as particles flow through the device, the sensor distinguishes biological matter from microscopic plastic polymers. It identifies synthetic debris originating from larger, degrading waste without any human sorting. By translating chemical and physical properties into direct electrical currents and optical scattering data, these nodes achieve parts per billion detection instantly. The manual laboratory bottleneck is entirely eliminated. Submerging optical and electrical equipment into a highly active biological soup introduces a fatal physical flaw. Organisms immediately begin attaching to the sensor's surface. This process is called biofouling. It starts as a conditioning film, progresses to dense bacterial microfilms, and culminates in catastrophic macrofouling, where barnacles and mussels encase the hardware. This biological crust doesn't merely block camera lenses and optical windows. A living layer of bacteria actively consumes oxygen and alters the local pH directly over the sensor. The device stops measuring the ocean water and starts measuring the biology growing on it. The first line of defense involves mechanical wipers that physically scrub the lenses before every reading, combined with material engineering, like super hydrophobic or liquid-infused porous surfaces that prevent microorganisms from finding a foothold. The ultimate architectural workaround is altering the geometry of the measurement itself. Advanced sensors utilize fluorescence excitation emission spectroscopy, a method that detects the fluorescent glow of organic matter from a distance, bypassing the need for exposed windows. While static point sensors provide deep temporal data, mapping an entire sea requires massive spatial coverage. Deploying dedicated, highly specialized research vessels to cover millions of square miles continuously is economically impossible. The logistical solution is the ferry box network. Instead of building new research fleets, engineers outfit existing commercial ferries with continuous flow-through monitoring laps. As the ship sails its regular commercial route, surface water is continuously pumped through the hull and routed into an internal sensor array. This system measures salinity, carbon dioxide pressure, and chlorophyll concentrations in real time. Because these sensors take readings rapidly while the vessel travels at high speeds, they generate an incredibly high spatial resolution, capturing distinct chemical signatures every few meters. When multiple commercial routes are mapped simultaneously over days and weeks, these individual lines overlap and intersect, generating a dense, live map of the entire sea. To protect the sensitive internal optics from catastrophic fouling, the systems are programmed with spatial awareness. When the ship approaches heavily polluted or oil-slicked port entrances, the intake valves automatically shut down, reopening only when back in open water. While the ferry box handles broad surface mapping, autonomous underwater vehicles, or AUVs, dive beneath the commercial lanes. Operating independently of ships, these robotic torpedoes map deep-sea chemical gradients and survey the topography of the seafloor. Piggybacking on existing commercial maritime infrastructure effectively crowdsources oceanography. It solves the spatial density problem, delivering millions of data points without inflating operational budgets. The final layer of the stack operates in orbit. Standard optical satellites can photograph massive surface pollutants, but they are blind half the time, entirely obstructed by cloud cover and nightfall. To maintain persistent observation, agencies rely on synthetic aperture radar, or SAR. These satellites utilize microwave pulses capable of penetrating dense clouds and operating in total darkness. SAR relies on the physics of Bragg scattering. Wind creates highly textured capillary waves on the ocean surface. When the satellite beams microwaves down, these rough waves scatter a strong signal directly back. When an oil spill occurs, the viscous fluid dampens the waves, smoothing the ocean into a flat surface. When incoming microwaves hit this slick boundary, they deflect away. Because the signal bounces away, the satellite registers a distinct radar void dark spot. This orbital absence of data matches the physical reality on the surface, where a viscous sheen suppresses the natural texture of the water. The operational challenge is that oil isn't the only thing that smooths the ocean. Natural phenomena like wind shadows, upwellings, and thick algal blooms also create smooth radar dark spots, leading to high false alarm rates for maritime authorities. Resolving this ambiguity requires deep learning. Researchers train advanced AI architectures like YOLO v4 using thousands of annotated radar images. The algorithm learns the subtle morphological differences and jagged edge patterns, separating a deliberate, illegal oil dump from a natural wind shadow. By integrating this automated classification, authorities can continuously track hundreds of illegal operational spills near heavy traffic zones like the Suez Canal. It isolates the exact coordinates of the pollution, removing manual human analysis and error from the equation entirely. When you combine these three tiers, you create a fully integrated diagnostic dashboard. Orbital radar tracks, mobile ferry box data trails, and alerts from deep-sea IoT beacons all overlay onto a single live map of the Eastern Mediterranean. This enables an immediate response cascade. A SAR satellite detects an anomalous dark spot from orbit. That orbital trigger deploys an autonomous underwater vehicle to investigate the depth, while local IoT sensors instantly confirm spikes in toxicity down to the parts per billion level. This multi-layered network operates against a backdrop of immense economic pressure. Navigational choke points like the Suez Canal manage a massive percentage of global trade, carrying the constant threat of operational spills and chemical runoff. The intensive coastal monitoring initiatives deployed by Egyptian authorities prove this architecture is not theoretical. It operates as a required active defense mechanism for the world's most critical maritime corridors. We are transitioning away from writing forensic reports on marine dead zones months after they occur. The new standard is proactive, algorithmic defense, capable of pinpointing violations the exact moment they happen. The ultimate achievement of this four-dimensional architecture is the creation of a collective, automated intelligence. It provides the exact spatial and chemical data needed to guide real-time human intervention, isolating the threat before the marine biome collapses entirely.